What's the benefit of calling multigrid twice? The benefit is solving the error equation more accurately. So multigrid is still a iterative method, right? So when we solve for example, do we still have U in memory? Yes, we still have U in memory. So if you call residual of UB, residual should be pretty small, but it won't be negative. So if you do norm of R, why is that? Okay, so let me see. U is equal to B times 0. R is equal to residual norm of R. Okay, sure. So the initial norm of R is huge. So that's actually the residual of the right-hand side. So that's the residual if you plug in a 0 initial condition. And if you do U equal to a multigrid U of B, so that completes one cycle, and you compute the residual again, the norm of R looks like reduced by a lot. It's less than 1% of the original residual, but it is not 0, right? So every time you call multigrid, it gets an approximate solution. It reduces the error of the solution, but not to 0. So if you call it again with the previous U as the initial condition, and I'll just say norm of the residual, it's further reduced by something like less than a little bit more than a factor of 100. So if you call multigrid twice, you solve the equation more accurately, right? You reduce the error more. And if you solve it, if you can afford to solve it 3 times, now the error is even smaller. And if you solve it 4 times, the norm is even smaller. Oh, good question. Did I change my code back? Oh, I'm now doing the W cycle. Yes, but like the effect should be. Okay, the effect. So you're asking which way is better, right? So first of all, let's take a look. Let's actually try it. So I commented this out so that I'm actually doing a V cycle, and you can see the residual is a little bit larger than in the previous case. The previous case I think is like 1 point something times 10 to the 5. Now this is 2 times 10 to the 5. So there is a little bit difference, not very large. And that depends on equation versus equation. For some other equations, maybe you will see a more dramatic difference. And also the cost of a V cycle compared to a W cycle. From this picture, it looks like a lot, but computationally, it may not be a lot at all, because once you go to a coarser grid, the cost of solving things on the coarser grid is reduced by a lot. So you have to compare the relative speed of reducing the residual versus the relative computation cost. You have a question? What's the convergence rate? That depends on a lot. So in your project, I encourage you to try a bunch of different things. The W cycle versus V cycle definitely makes a big difference. And the number of pre-smoothing iterations, for example, I can change this to 3 and change this to 2, right? And that'll make the cost much less, but the convergence may suffer a little bit. So if I change this and compute the norm again, yeah, so instead of 10 to the 5, I get 10 to the 6, right? So I reduce the cost, but like the convergence rate is lower. when you go down the grid, how do you? Oh, you mean the convergence rate of the Jacobi iteration? Does it change in the way? Oh, okay. So I think your question is more related to the eigenvalue structure, right? So the convergence rate of a Jacobi iteration relates to how close are the largest eigenvalue to 1 and how close is the smallest eigenvalue to -1. If you do any kind of under relaxation, then how close is the smallest eigenvalue to -1 doesn't really matter because you have a big gap. It's really related to how close is the largest eigenvalue to 1. And the general rule for the Poisson's equation, we are going to actually do some analysis later on. The Poisson's equation, the gap between 1 and the largest eigenvalue goes like 1 over n squared. So if I have this, oh, I don't have this anymore. So if I do n equal to 124 and compute the eigenvalue of r, and 1 minus the eigenvalue of r, we get this value. This value times n squared is roughly constant. In this case, it's roughly 5, right? So if we reduce to n equal to 8 and do the same thing again, and multiply this with n squared, it's also about 5. So over a big range of grid size for Poisson's equation, the rate of convergence is roughly inverse proportional to n squared. So if you make your grid bigger by a factor of 2, you expect the convergence to slow down by a factor of 4. Does that answer your question? That's actually one of the reasons Poisson's equation doesn't gain a lot from a W cycle, because on a causal grid you are solving that much better. Any other questions? Yeah, I like you asking questions. I think if you don't ask questions, it's as good as watching the videos back at home, right? So I think the real value of coming to real-time lectures is if you ask questions. I appreciate. Yeah. As you go cos and causa. Yes, actually. So the question is, as you go cos and causa, does it make sense to start using a different iterative, use a different method? So a lot of people, they find as you go cos enough, it makes sense to just use a drag solver to solve the equation, right? So if you go down to something like a few hundred by a few hundred matrix, solving the matrix using a drag method is actually a lot faster than solving it iteratively, and you get an exact solution. So that is because as you go cos and causa, the relative sparsity of your matrix actually decreases. So if you have a 1 by 1 matrix, it's 100% dense. Like, why solve it using iterative method? Another consideration is if you are solving this in a huge parallel machine, you just can't cosin to a 1 by 1 grid, because if your solution is distributed among many processors, then at some point you need to start doing something differently, because now each processor may only have like a few, like non-divisible by 2 number of grid points. So you need to start doing things like transferring the solution to a fewer processors and things like that. So it makes sense to do something different as you go to cos enough.